Hello guys, today we're going to go over conditional probability. It's 5.3. It's a somewhat theoretical and somewhat mathematical chapter, but it's pretty interesting, not that difficult. Let's go over the first definition, talking about conditional probability. Now, conditional probability states that, the probability that one event happens given that another event is known to have happened. That's called conditional probability. Again, there's a condition involved, and the condition is that the previous event has happened. Okay, this could be theoretical or experimental, doesn't matter. You just use the value of the previous event. The conditional probability that event B happens, given that A has happened, is denoted like this, and it's an actual division. If you look at the word problem in the following page about the Titanic, it says that there's survived, there's died, then there's classes first, second, third, and then total. So for example, if they tell you, let's change this TS, and again, the first question says, well, let's read the word problem. In 1912, the luxury liner Titanic on its first voyage across the Atlantic struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. The two-way table of information on adult passengers show who survived by class of travel. Suppose we randomly select one of the adult passengers from the Titanic. Define the following events. F is a first-class passenger, S is survived, and T is a third-class passenger. What this denotes is pretty much what are the chances that what are the chances that you were in third class and survived? The conditional event being you had to have survived. So if you were from those that survived, what is the probability that you were in third class? So you find the values. Third class is 151. And then the survived, which, should have happened or happened, is 442. You divide, and that's the probability of being in third class and have survived. Again, pretty straightforward. I don't think it's that difficult. Let's go over the next green box, which is very important. It's incredibly important. In this chapter, we're dealing with dependent and independent events. Now, independent, let's give you just a really basic definition, then we're going to go into detail. An independent, or not an independent event, but independent events, because there have to be more than one, are events that doesn't matter what happened previously. There's no, it's not going to change the outcome of the following event or experiment. So for an independent events, previous events have no meaning, no impact, nothing at all. For dependent events, they do matter. Okay. Now, let's go, for example, in the exercise that they give us, and they say, pierced ears. Let's actually copy it. This is pierced ear, yes or no, and this is gender, assuming binary gender. Don't kill me. We have male and female. Let's go 1971, 90. I'm not assuming that's what's in the book. 84, 488, 103. Again, this is a two-way table. These are the marginal frequencies. You should already know this and also be used to my very ugly numbers. 178. Now let's go over a particular example. Let's go over the first one. It says, let's read it. The chances involved of randomly selecting a student from college statistics class. The events of interest were: is male and has a pierced ear. Is male and has a pierced ear. Now, it says, it's asking, are these events independent? And the probability of a male that has a pierced ear, is, according to the book, 211. And a female having a pierced ear is a lot bigger. It's 0.955. So again, when you have to evaluate a certain group of events to determine whether they are dependent or independent, you have to ask yourself, was the previous event, did the previous event change the probabilities of the following event happening? And it does. I mean, selecting a different group greatly modifies the outcome. So the previous event, being male or being female, will definitely change the outcome of having a pierced ear, which is the following event. So selecting a male that has a pierced ear versus selecting a female that has a pierced ear, the second event is the same. But the first event changes the probability of the second event happening by a lot. So again, these are selecting a male that has a pierced ear. These are selecting a female that has a pierced ear. Chances are quite different. Now let's go over another independent event to give you a comparison. Again, we're gonna toss a coin in the air and then determine whether, whether you roll a 1 on a 6-sided die, okay? So the probability of the first event happening is 0.5, and the probability of the second event happening is 1 in 6. So it doesn't matter if in the first one the math will be exactly the same for the second event. It's always going to be 0.5 times this. The first event has absolutely no impact on the second event. But having a pierced ear, being male or female will have a pretty big impact on whether you have a pierced ear or not. So the first event, gender, selecting a male or selecting a female, will give you a vastly different probability of finding someone with a pierced ear. So again, that's a comparison of independent versus dependent events. Again, to wrap it up, independent events, previous events have absolutely no impact on the probabilities of following events. And on dependent events, previous events do have an impact on subsequent or following events. The name kind of tells you what's happening. The math involved, however, is slightly different. Let's go over the general multiplication rule. Again, they give you a whole bunch of numbers and letters, set theory, symbols, union, intersection. It's not that difficult, pretty much. Let's go over the green box. It says the general multiplication rule. For any chance process, the probability that events A and B both occur can be used using the general multiplication rule. Pretty much the probability of A times the probability of B happening, assuming A has already happened. So all you have to do is multiply these two. The big difference is this denotes a conditional event. Okay, you're assuming B if A happened, and then the probability of, let's go in order. Probability A, the probability of A happening, and then B when A happened. This is how you multiply conditional events. We're gonna scroll a little bit further. I'm gonna do a jump here. I'm gonna jump the next green box and let's go to the following to go over multiplication of independent events. And for independent events, it's pretty simple. You just multiply the probability of A happening and the probability of B happening. These are independent. The first one has absolutely nothing to do with the second one. So when you're talking about independent events, you just multiply the probabilities, and that's the probability of both of those events happening. When there is a conditional probability, it's the probability of the first happening times the probability of the second happening given that the first happened. And again, that's a division. You multiply that, and that's the probability of this happening given that this has already happened. So the top one is for conditional, the bottom one is for independent. Pretty straightforward. Now we're gonna go over tree diagrams, which are pretty useful to find, conditional probabilities or probabilities that have different stages. Now again, they give you a certain, certain like values. Then they said, hit the snooze button. That's me. I hit the snooze button too many times. I think that was a very bad invention. It just helps people be late. And you don't hit the snooze button. Then here, again, they give you different numbers. And this is pretty straightforward. Many of you already did these tree diagrams when, 8th grade, 7th grade. But let's do a quick review. On time, late. On time and late. So again, tree diagrams, and again, these each have 2 outputs, but you can have more than 2 outputs. You can have multiple outputs. But pretty much, this tells you the probabilities of some events happening, given that a previous event has happened. So these are definitely conditional probabilities. For example, you can tell that they are conditional probabilities because these are being on time. But the probability varies based on whether you hit the snooze button or you don't hit the snooze button. So tree diagrams are very easy ways to tell whether some probabilities are conditional or not. So again, if they tell you, what is the probability of being on time and hitting the snooze button, well, you got it right here. You can just use the tree diagram to plot these things out. Give me 1 second. So for example, they give you an example. They ask, what are the chances that you don't hit snooze and that you are late? So the chances that I do not hit snooze are 0.4. And the chance that I'm late is 0.10. One second. Okay. Just trying to check simple multiplication. Give me 1 second. Yeah, it says the probabilities of the first stage after the first stage are conditional probabilities. So that's pretty much it. Used to find conditional probabilities. Now, this is finding, let's see, because again, it says hitting the snooze button and being late after you hit the snooze button, 0.3. Okay, is that the math? The math wasn't adding up. I'm sorry. The math wasn't adding up. Because again, remember one thing. When you do conditional probabilities, you're stating the probability of an event happening after an event has already happened. And you have to do a division. Here, they're not doing a division because this has already taken into consideration that the first event happened. So what they're giving you here are the actual conditional probability values, so no division needs to be done. That's why I was a little confused. I apologize. I was just confirming. And that's pretty much it for the chapter. If you have any questions, please let me know.